Thank you all very much, and thank you, the organizers, for inviting me here. It's always a pleasure to be in Seoul. So I'm going to talk about geometric deep learning, and the beginning of the story is what we understand as all like a classic deep learning. So we have seen today, this morning, two very nice keynote talks that told us some of the very impressive achievements that this technology have been able to deliver in the recent years. So for example, we know very well how to do magic things with computer vision, speech recognition, machine translation, robotics. So all these all these examples have something in common, namely that all this data, even though it lives in a very high dimensional space, is organized in a very nice way. So images they are defined over a grid of pixels that is organized in a two-dimensional regular grid. Speech signals are defined over a one-dimensional set of regular samples. The same thing goes for text, etc., etc., etc. And this actually is leveraged in a very interesting way by neural networks that are able to leverage this structure, like, for example, convolutional neural networks or recurrent neural networks. So today, the question that I'm interested on is, can we understand in a bit more like mathematical and fundamental way, what is the geometry, what aspects of the geometric of the data are being used by these models? In particular, how can we take this understanding and use it in more general domains? So what do I mean by more general domains? So we might be interested in doing learning over data that does not look at all like images or text. For example, we might be interested in understanding some patterns on social networks that involve, let's say, people or other things that we all see during the talk. We might be interested in what's called functional networks that study patterns of organization in neurons, for example, or proteins. We might be interested in doing better computer graphics, where data here really comes with some very natural geometric structure, but it's not in a regular grid. Or, of course, molecules and proteins, etc., they have also some very important geometrical structure, but it's, of course, not organized as before. So what kind of problems is motivating this study? So what kind of techniques or what kind of tasks we might be interested in and trying to do better with deep learning? So, for example, we might want to leverage a bit better recommended systems. So, how to actually recommend some items to certain people. We are also interested in applying machine learning for physics, high energy physics, for example, in the detection of neutrinos, or in particle accelerators to try to understand, to develop, to push the boundaries of physics. Also, in chemistry, there's a lot of interest right now on trying to do machine learning, for example, for trying to do a more efficient, like a functional prediction, or, of course, in computer graphics. And another important motivation from this set of techniques of geometric deep learning is this ability that it gives us a language to try to make networks smarter, in the sense that if we have some prior knowledge of some problem, we might want to be able to put it into the model, right? To basically tell the model something that we know about the fundamentals of the nature. For example, we might be able to encode some symmetries that we know of a system into the network, etc. And so, in general, what I'm trying to describe here is a picture where we need to think about doing machine learning over data that lives in some geometric space in a kind of a unified manner, right? So you might think, you might have some problems where the natural way to describe the data will be with a graph. So graph is a very general data structure that allows us to just capture relational structure between features. But in some problems, you might have actually a richer structure. So the data might be of the form of a manifold, for example. Think about it as a kind of a sheet, right, where you have some data defined over some continuous domain that can be moved. Or even more generally, going into this direction of more symmetry, you can even have data that lives in a domain that actually have a lot of symmetries. For example, in an image grid, right? And so what is interesting here is, can we think about doing machine learning in all these domains in a unified way? So just I'm trying to give you a little bit more, even more motivation of some instances of this problem, what I'm trying to do. So we might be interested, as I said, in solving classification problems that really look a lot like image classifications. So the input of this problem might be like some molecule, and one might be able to predict some function of this molecule. So this is like just a single label for the whole graph, the same way that this image is classified with a single label. There are some other problems that we call node-wise classification. So think about motivation. For example, I have a social network, and I might want to predict, let's say, the voting preferences of this network. Right? So basically now, in that case, for every node in the graph, I want to predict the label. And this, an equivalent motivation for this is, for example, segmentation problems, right? Where every pixel of an image can be associated with a label. But these kinds of problems, in a sense, offer even more interesting features. For example, there are some problems in which the domain, like the graph in which the data lives, is not fixed, right? So there are problems in which the domain is changing at every instance. For example, in this example of a computer graphics, where every time I have a new data point, the domain has changed. Or there are problems in which, on the other hand, the domain is completely fixed, right? Like if I have a social network or knowledge base, the domain is always there. And another interesting difference, another interesting variant, is there are some problems in which the graph, like the connectivity of the relational structure of the features, is known. You can measure it, and you can use it as an input. Versus there are some problems in which the connectivity structure is presumed to be there, but is not necessarily observed. Right? It needs to be inferred. It needs to be learned. So, for example, I will see some examples later of these two kind of applications that have different flavors. Okay, so today I'm going to try to introduce, to motivate a common way, a unified way to think about this problem through this notion that is like geometric stability. And it's going to be a slightly formal mathematical notion, but I'm hoping to give you, to be able to communicate the main message. And then we are going to see how this notion of stability, that it's actually one of the key driving forces of these structured neural networks, can be deployed, can be defined over all these general domains. And we are going to spend the second half of the talk describing some applications and hopefully try to motivate why these models, these architectures, should be useful across many disciplines. So let's start with a very simple setup that tries to motivate this notion of geometric stability for the case of, let's say, computer vision. So here, let me just illustrate this setup with a very simple image classification task where I have some input data, x, that every x could be like a different image. And I can see this x as a point in a very high-dimensional space, right? Like the number of dimensions is the number of pixels that I have in the image. And so the goal of supervised learning is to figure out, to estimate a function that maps images to some label, to some like this function f. And so in the supervised learning setup, I need to estimate this function only by knowing the value of this function in some data point, like the training points. So you have to think about this. Every one of these images is almost like a star in the sky, right? They are very, very far one from each other, right? So I'm trying to figure out to fill the space, and I have very, very little information. So the only way I can actually hope to succeed is to make assumptions, right? I need to understand what are the assumptions on the function that make this thing possible. Okay, so what is the assumptions on this function that make this problem be feasible? And so, despite the fact that these points x are points in a very high-dimensional space, they have something that is fundamentally low-dimensional, right? So if I think about an image, I can think it as a point in a million-dimensional space. But as I said, it's also a function over a two-dimensional grid, right? And the fact that this grid is two-dimensional brings a very key low-dimensional structure that we can leverage, right? And so try to motivate, think about this problem of what happens if instead take an image, and instead of adding noise to the pixel values, you are going to add noise to the pixel locations. So in other words, you are going to move pixels around. So if you do that, you see that you are able to create transformations where we know that our function f should be stable. In other words, if I move the pixels a little bit, the value of the function I need to estimate is not going to change too much, right? The content of the image, the semantical content of the image, is stable with respect to this form of noise. So one can actually quantify, formalize how much geometric noise I'm adding through this but like a notion of how much the domain is actually going to be being stretched. And this kind of a model, like a mathematical model of deformation, can be used to model, let's say, changes in point of view. When I look at an image from different angles, it can model local deformations, and it can also, of course, also be used in other signal processing applications. So the question, of course, is once I have this prior of the world, how can I leverage this prior with my machine learning model? So, of course, it should not be a mystery by now that a very efficient way to leverage this prior is to rely on look at the algorithms that actually work. So the algorithms that actually work is, of course, this convolutional neural network architecture that was developed by Joan in the 80s and the 90s. And by now, everyone knows what this architecture is doing. But essentially, it's just stacking a very simple operation and then again and again, which is basically consists in a bunch of local filters that are interleaved with point-wise nonlinearities. And so, of course, there are many nice things about the convnets. I just picked like my 5 favorite properties. So in particular, related to the kind of the topics that I described before, they incorporate this kind of global symmetry that we know that these functions that we care about are typically invariant to translations. They also have this very nice, they leverage the fact that many things that we care about have a multi-scale structure, so we can leverage this by basically reducing the image size with depth. And of course, the fact that the filters are localized in space, they have very, very small filters, it's actually what's related to this notion of geometric stability. So of course, now the question is, how can we now take this very successful architecture and extend it to a domain that is not a regular grid, right? So this convolution operation really relies very heavily on the fact that I have this regular structure in the input. So how can I extend it to a non-regular domain? So for this, and this is going to be just a slide. They're not going to be many equations, but there's just a little bit. Is we have to think about what it means actually to do a deformation and try to generalize it basically think it as an instance of something much more general. So if you think about a deformation, mathematically, you can relate it as a change of variables, right? I'm just basically defining a way to compare images, and I'm doing a change of variables. So if you do the change of variables, you see that when you compare two images after deformation, what you have done is you have changed the dot product structure, right? You have just changed the metric. So in other words, what we are seeing here is that once I have a domain where I have a notion of distance, in other words, technically speaking, when I have a metric domain, what I'm asking is that if the metric structure doesn't change too much, the function that I care about does not change too much, right? And this is what this equation is capturing. So of course, now what we would like is to try to think about this metric deformation in a more general domain. So for this, we need to replace our regular grid omega that I described here as omega. We replace it with a general graph that is going to be unweighted. So a graph contains a family of vertices and a family of edges. And now I think about my signals as living on a graph instead of living on a regular grid. And so how can we define a metric structure over a graph? That's the question. So there are, of course, many ways to do that. And this is actually by no means a new question, right? Many people have thought about this question in the applied math and the signal processing community. But a very successful notion of actually how to upgrade the graph from a graph to a metric space is to use this notion of diffusion distance, right? So diffusion distance, in a nutshell, we use the graph to define a random walk, which is basically a Markov transition kernel. And what we try to do is the distance between 2 points on the graph corresponds to if I let the diffusion process start at 2 points x and y, and I look at the probability distribution after time t, how likely are these two probability distributions to actually overlap to each other. Okay, so that's the notion of diffusion that basically generalizes the metric distance that we have on a regular grid. And so from that, we can define a distance between two graphs. Basically, we can just say that two graphs G and G prime are close if their diffusion metric structure is close. And so in that case, we can now ask the same question as before. How can we build a representation of our graph that if I change the graph a little bit, in the sense that this diffusion distance doesn't change too much, I would like my features not to change too much, right? That's pretty natural. So now we can really try to understand how to build these representations by going back again to the definition of a convnet, right? So if you remember, a convolutional network, as I said, consists in a number of layers, and the layers basically consist in these local filters. So you can think about these local filters as basically, in terms of these local operations that technically speaking are called local derivatives. So these local derivatives basically are the essence of convnets, right? This is the reason why these local derivatives, in fact, one can show that they are stable to deformation. And in a sense, a convnet now you can really see it as I start from a building block of operators that are stable, and now I'm allowed to do like basically a Tetris, right? I'm able to learn linear combinations of stable operators and interleave them with stable nonlinear operators, right? So the question, of course, is how can we take these local derivatives, like these directional derivatives, and define them on a general graph? So unfortunately, we cannot do exactly the same thing. But on a graph, we have something that is actually very close, and for all that matters, it turns out to be sufficient. So we don't have we don't have a directional derivative on a graph, but what we have is something very powerful that is basically a low-pass filter, a diffusion, right? So if you look at the graph and you consider the adjacency matrix, essentially it acts like a low-pass filter. And so once we have a low-pass filter, we can learn linear combinations of filters by basically learning for each layer a linear coefficient, a linear combination of a low-pass filter and a filter that basically just propagates the input. And this is actually a graph neural network, right? So it was not introduced using this formalism in the original papers already like 10 years ago by Scarselli and Marco Gori. So, but now this is a kind of a modern definition that you hopefully, I'm hoping that highlights the connection between the convolutional neural networks that we know and love. So this is a model that is actually very flexible. So we don't need the domain to be fixed, right? We can define it. Even the domain changes at every input data point. It has, in a sense, it went a little bit under the radar for several years until it resurfaced, like 5 years ago, and it has been modernized and used a lot since then. So graph neural networks are, and I'm hoping to just describe very briefly, they are very popular right now. So if you look at basically the keywords that are being most popular in the deep learning conference, there is like XLR. You can see that graph neural network is the keyword that has seen the most increase in usage, right? So in a sense, the derivative is increasing. And it's instead of a convnet being just a single architecture, here we have many different variants, right? So there are, if you look at this very popular repository on GitHub, you have 52 basic models, right? Which is basically 52 graph neural networks. Of course, there are more, and there are a lot of libraries that are building on top of very popular PyTorch and TensorFlow, etc., that develop these models. And what do we know? What can we know about? What can we say about these architectures? Well, here let me just mention very briefly some of the work that we have been developing recently with my collaborators. That has to do with a very, let's say, old and classic question that people ask in neural networks, right? That especially in the theory side. That has to do with this, what we call this universal approximation. Okay, so one can think about graph structure data as being just specifying a set of symmetries of the input, right? So, for example, if my graph was fully connected, like the thing that is displayed here, what it means is basically if I tell you that my data lives in that graph, essentially I'm saying that it doesn't matter the ordering of the features, right? And the only thing that you want is a function that depends on the population, right? It doesn't depend on the order. And so, in particular, one natural question is how can we organize their graph neural network architectures to make sure that they are capturing, that they are as powerful as possible while respecting these symmetries. So in this recent work, just to give you the little flavor, we developed a framework, like a formalism, that relates it to a very, let's say, a classic problem in graph theory that is called the isomorphism problem, right? It doesn't matter the details, but essentially it's a problem that asks whether two graphs are isomorphic, whether one can actually reorder the nodes of one graph so that it completely corresponds to the other to the initial graph. And so, based on this formalism, we are able to a little bit organize this zoo of graph neural networks, right? At least to try to organize them a little bit in terms of which one is more powerful than which other, and for example, which families of graphs different neural networks are unable to tell apart. Okay, and this is actually very recent work that will be presented next month. Okay, but now I thought that would be I would spend more time giving you a little bit overview of what can we do with these models, okay, and which applications we have been mostly focusing on. So one very promising and I think important area of application is what's called this computational drug design, right? In particular, like computational chemistry. So the problem in chemistry, of course, I'm not chemist, I'm no expert, but one of the key problems in chemistry is to be able to, in a sense, synthesize candidate drugs with the most efficient synthesis process, right? But in a sense, deciding this question is very expensive, very costly, right? Because we need to simulate, we can simulate the properties of a molecule at quantum level, but this requires very, very, very expensive solving a very, very what's called a Schrödinger equation. That is an equation that blows up very quickly, right? The number of degrees of freedom blows up very quickly, so it's very expensive to compute. So typically people rely on approximate techniques, but very precise, that is called this density functional theory, which is something that is like one step above the Schrödinger. But these techniques, while being very sophisticated and very nice mathematically, they're still very expensive, right? Relatively expensive. So graph neural networks have been used as a platform to basically pre-screen like large numbers of candidate molecules at a computational cost that is, substantially faster than the best known, like the density functional theory. So, and this is work that has been pioneered by some people at David Dubenon at Toronto, Justin Gilmer at Google, etc. Okay, so this is one area of application where I think graph neural networks are going to be very popular. So here also I give you some examples of, so this is a work that I haven't been involved in, where how can also one can define graph neural networks, not just to do some prediction problem, but also to even do like generation, right? So if we want to actually generate molecules, we can, we are doing baby steps to accomplish this problem, and this is like a recent work also by Simonovsky and et al. Another area where I have been involved myself, and I think also is full of promises of trying to capture this interface between structured deep learning and physics, has to do with high energy physics, right? So I'm going to give you just two snippets, two instances of it. So here I'm going to describe a little bit the experiment in the Large Hadron Collider, which is a particle accelerator in Geneva, in the CERN. And there you have a huge amount. So basically, you have a simulator that is so you have actually an experiment that is very, very large, as you can see here. And so there, the goal of the game is to try to distinguish, to actually organize different theories, like fundamental theories of fundamental physics at the quantum level, and try to actually understand which one is more likely than the other, right? And for this, physicists have developed very sophisticated simulation protocols that basically simulate what would happen if two particles crashed under theory A, and what would happen under theory B, right? But the problem is that solving it in the Bayesian way is impossible, because of course, these simulations are actually extremely complicated. So we rely on actually machine learning to try to bypass the posterior inference and just treat it as a classification problem. Okay, so here, each input, here it's a bit schematic, but you can see that every instance of the problem is a point cloud of what's called like a jet, that you can think it as points in a 6-dimensional space that involves a different momentum. And there the goal is to actually try to separate between two different theories. So that's for the example on the left. And then on the right, we have neutrino detection. So neutrinos are, as you know, like another fundamental particle that comes from basically from the cosmic rays. And so the scientists have developed this very impressive detector. This is actually a physical 1 cubic kilometer of ice, right, in the Antarctica. And so this, I mean, I don't know if you see it there in the corner, but that's the Eiffel Tower, just in the little thing, right? So just to give you an idea of what is the scale of this detector. Okay, so there, again, you have some neutrinos, and there is an interesting because you have very, very, very little signal, right? Like the number of neutrinos that are detected per year is actually pretty small. So in both cases, we have applied these basically graph neural networks that are able to leverage physics, right? So basically, when we define the similarity distance between features, we use different aspects of the theory. So on the left-hand side, we use kernels that come from quantum chromodynamics, and here on the right, we use more traditional like metrics. And as you can see, in both cases, the models the GNNs that basically are physics informed are able to significantly outperform the other models that are essentially a bit more agnostic to any kind of physical structure. Again, these are works that we published in the last few years. Okay. Another interesting application that might be a bit related to what Abhinav have been described on the keynote has to do with robots, and in particular, like the fleet of robots. And in particular, how can we use these graph neural networks to learn decentralized control policies, right? So in the case where you cannot rely on a centralized controller, and you have to try to organize a collection of robots. And this is work that I haven't been involved in. It's my colleagues, Fernando Gama and Alejandro Ribeiro from UPenn. So I'm just going to show you an example of kind of policy that have been learned by these graph neural networks. So this is actually robots that need to, in a sense, they need to do what's called a flocking, right? They need to merge together in a way that satisfies certain properties, right? They need to be basically traveling at the same velocity and try to preserve like a kind of a uniform distance, right? So this is actually an example of these graph neural networks being used in a pipeline that, of course, involves many other levels of complexity. But as soon as you have some system where you have agents in the system, and you introduce some kind of constraint in communication. For here, in that case, the fact that the controller is not centralized. Here, you can use these things quite efficiently. Another instance where we might have to extract structure from relational data has to do with something that is actually very important in many areas of machine learning, where you don't have the luxury to have a lot of labeled data. That have to do with what's called a few-shot learning, right? Few-shot learning is this problem of trying to leverage past experience to quickly grasp concepts, right? With very, very few examples. So here is an example where we cast this problem as, again, as learning some relational structure where the graph is not observed, right? So here I presume that the information to discover what is the label for this object x bar somehow needs to come from relation, like we're relating this image x bar with what I observe, right? And so in a sense, this is just it completely naturally fits into the framework of graph neural networks. So we just proposed this work last year, and at the time, this model was actually quite successful. Of course, that was like last year, and in deep learning time, last year is just, of course, a long time ago. So now, of course, this model have by then been surpassed by others. But in a sense, I'm hopefully trying to give you the essence that as soon as you can recast these problems of quickly adapting as trying to leverage relational structure between images, right? And this is something that you can naturally do with the GNN. Another interesting application is what we call a network community detection. So here, the goal of the game is to try to estimate some community structure in a network. You can think like a network of people or computers, whatever. And so here you can really see it as a knot-wise classification problem. And so again, using a graph neural network, we see that this knot-wise classification problem greatly benefits from the flexibility of GNNs, right? So if you are familiar with this problem, it's typically solved using a kind of predefined diffusion processes. For example, you can try to use, let's say, spectral clustering. But this, in a sense, can be thought as a very specific instance of a GNN where I haven't done any training, right? So the fact that now we have these data-driven diffusion processes, as you can see, gives a lot of improvements in practice. Another instance where one can use GNNs have to do with basically the like processing of 3D data. So 3D data, you can model it with a point cloud, but you can also model it with basically discretizing a surface, right? So the discretization of a surface can be seen as a graph that has an extra-oriented structure that is it's called a mesh. And so here we just demonstrate the ability of these models to do a temporal prediction, right? So as you will see in the video, how I can basically think about this problem as a dynamic problem, right? I have some 3D data that also has a temporal component, and I'm using these graph neural networks to try to predict into the future, right? Some kind of like a self-supervised learning in that sense. So here, as you can see, once I have these graph neural networks that use different differential operators, I'm able to actually have very much improved performance. Okay, another problem in which this technology has been also very useful is recommended systems. So in recommended systems, the goal of the game is essentially to, given some context, I want to be able to serve the users, right, with the projects that I believe are going to be useful for the user. Of course, and I need to combine two sources of information that have very different nature, right? So every user might have some features that are like specific to them. For example, the history of which product it has used, or items might have also some features. But there's another source of information that comes from the topology, right? Who is connected to who? Which product did you buy before, right? So what is interesting about graph neural networks is that they are very naturally able to combine the two sources of information, right? Like information that I have that lives at every node with information that I have that is the topology, how things are related to each other. And so this is a work actually by Yuri Leskovec and his company, Pinterest. And he showed like really impressive results, right? So if you use that kind of technology in the scale of Pinterest, which is like a very, very large graph of recommended systems, you can see that once you are able to combine both features and topology, you are able to get like much more meaningful recommendations, right? Like recommendations that are not just relying on the actual content of the image, but also are aware of basically where this user sits within the grand scheme of things. And in light of this thing, we have also worked on a recent project that tries to build on that kind of problem. And the question, in a sense, is what is the natural, like the most powerful, efficient way to combine these two different sources of information, as I described, right? We have, on the one hand, the features that live at every node, and with the topology. And so it turns out that one can actually even increase the performance of GNNs by relying on basically something that is called an attributed random walk, that essentially what it does, it tries to define a new connectivity. It tries to, if you give me a graph with some features, what this attributed random walk is trying to do is to define a new graph that is going to be larger, where this new connectivity, the connectivity in the new graph, will depend on both the original connectivity, but also the features of the original graph. And we are seeing some promising improvements on like a simple semi-supervised classification problem, semi-supervised learning problems. Okay, and another task where graph neural network geometric deep learning has been very successful, and I think it's also quite important, is work also by my colleagues Michael Bronstein and company that actually developed this work in the context of their startup, Fabula, that was acquired by Twitter. And essentially the goal, like the problem is actually quite natural, is how can we use, again, this power of combining node features with topology to solve like important problems in networks that also have some dynamical aspect. In particular, can we use these models to predict fake news, right? Whether some news that is circulating within a network is going to turn out to be fake or not. And it turns out that there's a lot of actually information in the topology, right? Fake news have a pattern of spread that is very specific that then can be leveraged by these models. Okay, and this is something that they demonstrated in this recent work that they did. And so we are also now in my group we are developing the same ideas, similar ideas, to solve a related task that is fraud detection. And so, in particular, focusing on financial transactions, right? So you can think about a financial transaction network as being a network of agents, right? So in this network, you might have bank accounts and corporations, etc. And every time there's a transaction, there's an event, there's an edge there. And so what we are currently working on is on combining recurrent neural networks with the graph neural networks to try to predict whether transactions are going to be fraudulent or not. And this is there's of course a lot of, again, very supporting evidence that fraudulent transactions also have a very, very distinct topological pattern, right? Like this is an example from what happened in the Enron crisis. That's something that was pretty bad a few years ago in the US. That has been, we're able to leverage actually topology to detect that there was something bad going on. Okay, so I'm just gonna wrap up because we have to go for lunch. And so just what I try to describe here is try to give you a little glimpse of this framework, geometric deep learning, that is trying to get some kind of a unified picture of doing deep learning on data that has some geometric structure, right? And of course, the stellar, the canonical example is CNNs on images. But what I try to convince you is that this methodology, you can generalize it very efficiently, right? You can think about this methodology over very different domains. And so there are a lot of interesting questions that my group and other of my colleagues we are developing. So there's a lot of interesting questions on the theory side. For example, can you actually relate these architectures to classical problems in statistical inference? So many questions that we are trying to solve here on graphs, they have been studied for many years in the fields of statistics and applied math. And we are seeing that some of these questions can be maybe revisited with graph neural networks. Another interesting question is also how can we push this program of building networks that are more intelligent. So just to give you a motivation, there's recently a lot of interest on developing a deep learning for quantum mechanics, right? Try to actually have better estimates of wave functions using deep neural networks. So one of the big limiting factors right now is, for example, how can we encode what's called the fermion symmetry, right? The fact that two states cannot, basically when you swap two states, the wave function needs to change sign, right? So how can we develop these kind of symmetries, like models that are aware of the symmetry, in different applications? And of course, another interesting question is the robustness of these models with different adversaries. And of course, in terms of application, I try to cover just a tiny bit, but as you can imagine, there's a lot of situations where one might be confronted with some kind of relational data, and how can you actually best extract information from relational data? Well, here's a framework to do that. So with that, I would like to thank you very much, and I would like also to thank Samsung that was partially funding most of these projects. So thank you very much, and thank you to all my collaborators as well.